Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to really dive in to try and look at the chemical potential of mixtures. So just like we were able to use chemical potential to describe phase transitions, chemical potential is also going to be really good when we're talking about mixed component systems. But to do so, we have to try and define the chemical potential in a little bit more robust of a way than we did for pure substances. So we can treat our mixtures using this important partial molar property, chemical potential. And notice that the form here looks kind of similar to what we saw with partial molar volume from last lecture, where the chemical potential in its full description is going to be looking at how the Gibbs free energy changes as I add or remove a amount of the component of interest. Now we're doing this under fixed pressure, temperature, and amount of other substances. Now, just like last time where we saw that the volume could be simply calculated from the sum of the partial molar volumes, similar here, we find the free energy uh, from adding 1 mole of J will increase the chemical potential by of J, free energy of J. We can do the same approach to derive the Gibbs free energy for a mixture as the moles of each component times its chemical potential. And it's this version that we really use when looking at phase transitions. But it's this differential form also becomes really handy because we can go ahead and incorporate it in our fundamental free equation. So we know that the free energy changes with pressure and temperature. We saw that when looking at our fundamental equation for Gibbs. But I also mentioned at the time that what it lacked was how we deal with open systems where moles of a single component was allowed to change. And that's really incorporated here. But I also said it missed how reactions worked. And reactions work by decreasing the amount of one component and increasing the amount of other. And we get that from this form. So we now have our full equation for the full fundamental equation of chemical thermodynamics, where we can look at how the Gibbs free energy changes based on pressure, temperature, but most importantly, composition of the mixture. And again, this works by using this differential form of Gibbs, where we're keeping pressure, temperature, and all the other moles constant. And thus, we can simply get our Gibbs from each of these individual components, which is what we're showing here by assuming no change in pressure or temperature. So we also can use our fundamental equation to actually determine our chemical potentials from our other thermodynamic functions. So right now we have it in terms of Gibbs. We can also determine it from other properties such as internal energy. So we can do so by knowing that we can get the internal energy by just taking the change in Gibbs minus dPV plus dTs. We can do the same thing for enthalpy and Helmholtz as well. Now, when we do this, we end up with this uh, with our change in Gibbs minus PdV minus VdP plus SdT plus TdS. Again, just literally expanding this term. Now, when we do this, we can again look for canceling terms. Because when I insert the Gibbs, because I don't quite have enough space to do this on one line, we'll notice our VdP term cancels out here, our SdT term cancels out, and we're going to be left with these terms plus our chemical potential terms. So this gives us a new full fundamental equation. We now have the fundamental equation in terms of internal energy, where now we're finding that it varies based on volume, entropy, and composition. Now, the fun thing is that we can then also use this to define the chemical potential in terms of internal energy by keeping other variables constant. So the internal energy is going to be looking at the change in moles by keeping volume, entropy, and all other species constant. And indeed, that's exactly what we see. So internal energy is so chemical potential can also be calculated from changes in internal energy under constant volume entropy and moles of other components. And we can repeat the same process. Again, Gibbs is the same idea, but with pressure, temperature. Enthalpy is the same thing, but with pressure and entropy. And Helmholtz is the same thing with volume and temperature. So again, the two versions we're going to use the most are going to be Gibbs and Helmholtz, whether we're doing isobaric or isochoric conditions. And this is one of the reasons why, as chemists, we like to use Gibbs, because we tend to operate under isochoric conditions, making it easier to determine these chemical potentials, which, as we saw, really are going to dictate the compositions of a system. So we can kind of go back and again, showing that we can use our free energy expression to go ahead and determine the whole free energy based on the amount of both of our components and their chemical potentials. Now we can use this to figure out what happens as the composition of a mixture changes. So as I increase, what's going to happen if I change the chemical potential of one? What's going to happen to the chemical potential of the other? Now, if we assume the composition changes slowly enough, we can treat the amount of both components relatively constant. So we can fix our two component amounts and allow Gibbs potential and our two potentials to change. But remember, if we're doing a slow change, this is another way of saying reversible. And if it's reversible, we should be able to keep the system at equilibrium the entire time. So Gibbs is just going to be zero, which means as I'm changing composition, I can relate the change in chemical potential of one component to the other. And again, you can often think of this as solvent and solute, relating them to each other. And by, let's say, solving for the chemical potential of the solute, we find it's going to be negatively related to the chemical potential of the solvent. So if the solvent is becoming less stable, the solute is becoming more, and vice versa. But also notice we have this ratio term in terms of amount. So if one component, say the solvent becomes stabilized, that means that the solute becomes destabilized. And this is going to be because of the composition, because we'll typically have more solvent than solute. If I slightly stabilize my solvent, it means I'm going to be multiplying this by a large ratio and greatly destabilizing uh, the solute, and vice versa. If I have a large stabilization in the solute, I'll have a small destabilization in the solvent, because again, mediated by this ratio. Now, this is what it looks like for a two-component system. But it turns out we can relate this to a multi-component system using something called the Gibbs-Duhem equation. By simply adding together the amounts of each of the components times their chemical potentials, all of those should add up to zero, again, assuming slow change. And it's worth noting that, remember, we started with this idea that the chemical potential had a very similar formalism of the partial molar volume. And it turns out we can apply the same exact theory to the partial molar volume. And as we ended last time with this idea of comparing the molar volumes of a solute to a solvent, we can do this by looking at potassium sulfate and water. So as I add potassium sulfate, we tend to see that it increases in volume. As I add it, it's taking up volume. But it's doing so by shrinking the volume occupied by water, leaving a relatively constant volume. But notice, because we're looking at relatively small concentrations, again, less than 0.1 molal, that means that if I have a huge change in volume by the potassium sulfate, well, the water only has to change a little because there's so much more water that every mole of water experiences a small change, where every mole of sulfate experiences a big one. And again, all related through this general ratio of changes in one property versus the other. All right, so next time we're going to really look at the favorability of mixing a reaction using what we now know about chemical potential and defining our concentrations based on mole fractions to look at how favorable it will be to mix substances. Until then, take care.